Welcome to All Things Photonics, a podcast about the physical science of light driving scientific innovation in the 21st century. I'm Joel Williams, Associate Editor at Photonics Media. Join us as we explore the latest trends in optics, lasers, microscopy, and spectroscopy. Each episode, you'll hear from leading voices from across the photonics landscape, brought to you by Photonics Media.
In this episode of All Things Photonics, we bring you something done only once before in the history of the podcast. For the first time since Season 1, Episode 3, we've put together an episode hosted not in our offices, but on the trade show floor. It may not sound like much. Our plan when we launched All Things Photonics in January 2020 was to deliver multiple episodes each season from on-site at conferences and exhibitions. A pandemic, which ultimately became an every season theme for us, shuttered that idea while the podcast remained in its infancy. It's not the first event that members of our editorial team have had the chance to attend this show season, but Optica's Frontiers in Optics and Laser Science was the perfect forum around which to build this episode. From exhibiting companies including Hamamatsu, Viavi Solutions, and NKT Photonics, conversation topics on the trade show floor span timely advances in a range of laser-enabled applications, including optical and data communications. Companies like Optica and Vescent operated both as exhibitors and presenters, contributing expertise on quantum science, from quantum compute and networking to timing and sensing. Off the show floor, an end-user workshop coordinated by Optica CTO Jose Pozo brought industry leaders from a host of optics and photonics sectors together to spark collaboration and drive progress. The conference also featured the reveal of the 2022 Optica election results, Luminate Accelerator Finals, and the announcement of the Theodore W. Honch Prize in Quantum Optics. Up first today, we'll air a portion of our interview with Dr. S.J. Ben-Yu, Distinguished Professor in the Department of Electrical and Computer Engineering at the University of California, Davis, and a member of the joint faculty at Lawrence Berkeley National Lab. A leading mind in the fast-evolving integrated photonics space, we caught up with Yu in the moments following his presentation entitled Neuromorphic Computing with 3D Electronic Photonic Integrated Circuits. In addition to his presentation, we asked you to reflect on the 12.5 years since publication of a paper that introduced a method for real-time optical waveform measurement. The development was widely regarded at the time as a breakthrough step in the measure of ultrafast phenomena, and we asked you about progress in that area. Less than a year ago, Yu was also named as an inaugural participating researcher in the newly formed Intel Research Center for Integrated Photonics for Data Center Interconnects. We spoke with Yu on that work. That interview kicks off today's episode. Up next, from Frontiers in Optics and Laser Science in Rochester, New York. So we're with Dr. Ben-Yu. He is a joint faculty member, Lawrence Berkeley National Lab, distinguished professor, and director in the Department of Electrical and Computer Engineering at UC Davis. I want to start by going back, if we can. 12.5 years ago, you led a team that managed to combine spectral splicing with optical signal generation to scale up to 10,000 times the speed of standard electronics at about 10 gigahertz. Ultrafast phenomenon, in the time since that paper, 12.5 years ago, there are more ultrafast phenomena to measure and increased ways to do that. I want to get your thoughts on where we've come in 12.5 years since that paper in that area.
Oh, that's interesting. So thanks very much for reminding me of that paper. One thing is that there are two things. One is that commercially, this has taken off in the sense that the coherent communication world has realized that spectral slicing-based communication has become a thing to do, and you can generate arbitrary waveform of any coherent spectrum with any spectral slice. And we call that flexible bandwidth networking or elastic optical networking. And commercial companies adopted those, and it's everywhere now. So that's really exciting. And on the other hand, scientifically, people realize that this is scalable, and people have been looking at this in the X-ray to UV to optical, and there are a number of researchers working in this area. And I'm quite happy about this, both the commercial and the scientific world picking up on it, and my group is also working on some of that step by step.
Your presentation today, and here we are at Frontiers in Optics and Laser Science, presentation just a moment ago considers a pair of, we'll say, applications, neuromorphic compute and photonic integrated circuits, integrated photonics, that both independently are really well positioned to be popular topics in the literature moving forward. And you did touch on this in your presentation. What's the desire to pair neuromorphic computing with integrated photonics?
Okay, there are two answers to that. Number one is that we are relying quite a bit on the data centers all the time. And you have a thin client like a cell phone interfacing with the big data centers. And then you realize that a lot of times you actually want to have more privacy and more bandwidth. For instance, when you're driving a car, your autonomous vehicle may have to process 10 terabit per second worth of imaging and information, multimodal information. You cannot really rely on sending that 10 terabit per second type of information to data center and expect that that can come back to you to make a intelligent solution like avoid that person and avoid this collision and so on. That's number one. And number two is that the security, like, a lot of times medical doctors look at these images and so on, but then those type of images, let's say human brain image of, say, 1,000 by 1,000 by 1,000 pixels and 12 bits of color, and then if you have a 30 frames per second type of image interaction for the telemedicine, that is already a multi-terabit per second application. Now, how do you make decisions quickly on those things? You cannot rely on data center to do everything. So if you have a human brain that is artificially created and being able to learn from its experience in a very smart way, like a human brain can do, a lot of these things can be done locally, and that neural computing can be really exciting. On the other hand, though, people who have been doing this neural computing with CMOS or new generation electronics are finding out the scalability in terms of interconnectivity and scaling to a large scale, because you have to rely on electrical wires. And optical neural computing is taking off now because a lot of things you cannot do with electronics can be done with optics more in parallel, more scalably, more energy efficiently.
So it sounds like we have a couple of distinguishers here. One, we have the fact that we're placing quite a bit of reliance on the cloud, let's say that. And you also have CMOS neuromorphic computing versus electronic or nanophotonic, shall we say, neuromorphic computing. When we talk about neuromorphic computing, and this is through our very narrow lens, we talk a lot about maybe machine vision applications. Companies like Prophecy come to mind. But given the fact that we're placing a lot of reliance on the cloud, and in lieu of the presentation that you just gave, it seems like there are quite a few possibilities to incorporate neuromorphic compute into integrated photonics, and really photonics as a whole.
Yeah, exactly. What's interesting is that a lot of systems are moving towards the domain-specific computing. When you have a domain-specific computing, even with the electronics, you can get about a factor of 50 improvement in energy efficiency and throughput. So you can actually see a lot of these accelerators coming in. Photonics can be an accelerator in the electronic domain in the sense that you can do, for instance, Fourier transform or convolution very easily with lens or lens array type of stuff. But they're not really general purpose. So the talk that I gave today was emphasizing general purpose optical computing, like a human brain type of really being able to solve general problems, being able to abstract, associate, and come up with some creative solutions with optics. And optics being the key player here, that's really exciting because of scalability and so on. So in order to make the general purpose neuromorphic computing, we have to think about the new architecture, new algorithm, bioplausible, bio-inspired, or even in my case, bio-derived algorithm, and putting this photonics and electronics together at nanoscale, imitating this human brain type of stuff. That's kind of what we are working on.
I think it came out in December last year. It's been about a year, but you were named one of the first 7 researchers selected to participate in Intel Labs' Integrated Photonics Research Center. I want to pick your brain a bit about that work. How's that going? It's quite a project, pretty diverse set of projects and researchers selected for it. John Bowers was one. It's been about a year. How's that work progressing?
Oh, it's working very, very well. Thanks for asking that question. So that work is more about data center photonics, so photonics in data centers. And data centers are right now using von Neumann computing. So basically you have processor, memory, and interconnects. And the work is to enhance the interconnectivity with silicon photonics. So as you pointed out, there are 7 faculty members involved in it. And our group has been making really exciting progress in athermal silicon photonics with scalable to way beyond terabit per second. Working with Professor Sam Palermo at Texas A&M, we do co-integration, co-design of photonic electronics together to achieve energy efficiency that is about a factor of 10 to 100 times better. What's interesting is that 12, 13 years ago, we were also at the Intel Center. Again, Professor Bowers and Mingwu, myself, and a few other faculty members. Back then, the problems were very different. Back then, Intel was not really selling much of the silicon photonics. So back then, also, electronics people were thinking that electronics can do fine. There are a lot of companies like NVIDIA and so on. But now, the consensus 12 years later is that photonics is a must. Scalability is a must. Data movement is a must. So then the technology we're developing for multi-terabit per second times multi-fiber, multi-core, so approaching terabit per second type of communication for data center at the energy efficiency 10 times, 100 times better, that is going to be instrumental in the future data centers. On the other hand, the presentation I gave today was about neuromorphic computing. So the first intercenter is about phone-neural computing, how to facilitate this data movement. Well, as the talk I gave today at this FIO LS conference was the fundamentally different architecture with photonics in it. So you have synaptic interconnects with neurons so that you don't actually have the memory processor interconnect. You have everything lumped in like a human brain. So it's a very different architecture. And in this case, too, you need lots of photonics.
The diversity of pursuits for Ben Yu has literally veered into space. As a researcher funded by NASA's Earth Science Technology Office, Yu has been tasked with the challenge of using his expertise to replace traditional large telescopes with smaller, less bulky instrumentation. Before the James Webb Telescope in the mid-2010s, that objective for Yu fed into the development of the Segmented Planar Imaging Detector for Electro-Optical Reconnaissance, or SPIDER instrument. Will Yu tells us about that work? Our focus is on the far-reaching topic of the role that integrated photonics has to play in space imaging and exploration.
There was a plenary speaker today talked about the new generation of Webb telescopes and so on. We have NASA project. We have 4 NASA projects, and they are all addressing the fact that you want to be able to image and also make intelligent decisions based on the imaging with a very low size, weight, and power footprint. Because when you have to send out this Hubble telescope or Webb telescope, you have to have a humongous the rocket because the payload, the telescope is so heavy. Now, our photon integrated circuit-based telescope, we have several approaches. One approach is to do imaging in the Fourier domain. So instead of having big metal-based mirrors and or glass or some dielectric lenses and so on that will have to be on a big tube, we can actually do this with the photon integrated circuit on a wafer scale or on a blade and so on. So the SPIDER you mentioned is based on blade. We have a blade that gets put together side by side. That reduces the size and the power by about a factor of 100. The SPIDER Web that we're creating is an entire wafer scale that makes a imager that would have additional factor of 10 improvement. And then the new project we're working on is compressive imaging. You have all these advantages, plus being able to do hyperspectral imaging with the same resolution. For instance, if you're doing 1,000 by 1,000 two-dimensional imaging with 1,000 colors, then you need 1,000 by 1,000 by 1,000, 1 billion sensors or measurement instruments. Whereas in our case, we can actually do compressive imaging of hyperspectral spectral information with the imager, so that we can do 2,000 by 1,000, can do the same thing as 1,000 by 1,000 by 1,000. So you have factor of 500 reduction in the complexity. So the data you send out from the satellite down to Earth, first of all, you need 500 times fewer number of bits to be transmitted. Number two, you have already a very small size, weight, and power footprint when you can actually do the same, say, high spectral and resolution and high spatial image resolution. So I think the future imaging will completely change by this new photon integrated circuits into the imaging systems, and then incorporating the other things you mentioned about energy efficient silicon photonic communication or energy efficient neuromorphic computing, and then the energy efficient communication and so on, that will all come together and come to a very exciting future world of photonics everywhere in computing, networking, and imaging.
For 5 cohorts over the course of 5 years, the Rochester, New York-based Luminate Accelerator program has helped support over 50 startups through their journeys of product development, funding, commercial launches, and expansion. Benefiting from the Rochester optics, photonics, and imaging ecosystem, companies progress through the accelerator in competition form, balancing their development with the quest for up to $2 million in follow-on funding at the conclusion of the cohort. Luminate portfolio companies have a collective estimated value of more than $400 million and counting, and have raised an additional $127 million in funding. The 2022 finals, hosted at Frontiers in Optics and Laser Science, shone the spotlight on cohort 5 companies. Lydrotech, a German-founded company that develops wafer dicing laser technology for the semiconductor industry, emerged as the day's biggest winner, securing $1 million in follow-on funding and Company of the Year honors as the winner of the cohort. Lydrotech's technology enables thinner cuts with a virtually 0% damage rate, providing significant cost savings and productivity increases. The technology's innovation involves the efficient use of liquids in the laser processing zone that cool and rinse wafers while the laser cuts out the chips. The resulting benefits include thinner cuts with higher precision, no damages to the material, clean surfaces without debris, and higher processing speeds, all without the need to adapt to the production process. Alexander Eagleman, CEO of Lydrotech, was on hand to accept the award and discuss the company's technology and next steps. We caught up with Eagleman, joined by Luminate Managing Director Sujatha Ramanujan, following the ceremony. For the first time in 3 years, companies working through the Luminate program had the chance to operate largely in person, capturing the full benefits of the Rochester ecosystem. That, coupled with the continued embrace of the societal challenges of today, give each cohort a distinct flavor, as indicated by the innovative solutions and technological innovations they bring to the optics community.
Every cohort is the same in some ways, different in other ways. You've done this now 5 iterations. Can you characterize this year's cohort?
So this year's cohort was very international, and I think really bonded well, right? So I think we've been through a couple of different flavors. The first couple of cohorts were fully in person. We all were residential, and they had a certain energy to it. The second 2 were remote and COVID, and I don't think anybody really ever met each other. But this cohort, really, they got to hang out together. They got to really experience New York also, which was really, really important, that they got to come here and spend a significant amount of time with vendors, with the region, to understand why a business can develop well here. And so I think that the energy was really, really good for this cohort.
You've done this now, unfortunately, several times in the midst of a pandemic. At the beginning of the pandemic, and increasingly maybe in cohort 4, we saw some technologies aimed at applications that would support what's happening globally, and that's not surprising. You mentioned that this is a cohort that really bonded. Is that something that's unusual, or is this really the first time that we've seen that now, that there seems to be more cohesion?
They always seem to get along, but this one's particularly cohesive, and it's a difficult thing, right? Everybody's competing, so there's only, you have to be friends, and at the same time, you want to win, right? So that can be a little bit trickier. But I want to take a second to actually properly answer your first question on more than just the general environment. Each cohort has had a different flavor of what they're bringing to the optics community. And early on, we had a lot more medical tech, medical device, pharmaceutical research, because that was kind of the trend of what was happening in the industry. Then when we went to more remote-based applications, I started seeing a lot of what happens remote, what happens in those kinds of needs. And an interesting note, companies that were VC-backed and had investors survived the pandemic with more ease than those that were completely running on revenue, because those that were completely running on customer money didn't get any. And if they were on the edge, they were really struggling. So these kinds of programs like this really helped keep businesses afloat. This cohort is really, I can see a lot of supply chain addressing, a lot of critical issues of the world right now come out in the innovation that these entrepreneurs bring forward.
You mentioned semiconductor, and Alex, I'll turn to you, Alex Eagleman. Congratulations, because earning $1 million as the winner of the cohort.
Thank you.
It's hard to talk about semiconductors or semiconductor manufacturing right now. They're talking about recent legislation. I'm not going to ask you about that, but I do want to ask you what it's like to be a startup in that space face right now, given the supply chain situations and the fact that this is such a hot button issue?
Yeah, the supply chain issue is on the one hand a positive and a negative. I mean, the negative, obviously, we are also affected by the supply chain problems. You know, we have lead times for certain products that are beyond reasonable. On the other hand, of course, we can use that story for us because we are actually helping to reduce the chip shortage with our technology, because we can cut chips with better quality and therefore get more chips out in the production and increase productivity. So, you know, it has two sides, this point. But yeah, of course, I mean, the supply chain problem right now is big.
You're a German established company. Talk about moving your organization, or your operation rather, here to Rochester, the benefits that opens up for you.
Yeah, we have. I mean, we founded the company in Germany. We were a GmbH, it's the German entity, and we're still there. But we actually have a US entity now, Inc., a C Corp. So we already prepared the move here, and the US is a huge market for us in the semiconductor industry. I mean, if you think about the biggest semiconductor company, you'll think of a US company. So it's clear that we need to target this market.
Looking to the future, albeit 20 minutes after the conclusion of Cohort 5, Luminate's next cohort, number 6, is sure to be characterized by the reality that optics and photonics are core enabling technologies. That, Ramanujan says, makes innovation in those areas not only pertinent to society, but vital to critical need industries. One of those, of course, is the semiconductor industry. And with a freshly earned $1 million, Eagleman says the company has already identified next steps in growth areas.
So I think what you're seeing is an underlying theme that optics, photonics, and imaging is a core technology to just about every industry. So whenever we're looking at those critical need industries, it's something that has to happen. Almost always there has to be some innovation in optics, photonics, or in imaging to enable those solutions to actually useful and hit the market. So I think that we're seeing that enabling piece of optics come out in each industry.
I jumped the gun. I want to get your thoughts just again, 15, 20 minutes after finding out that you've won. How do you feel, and what's your immediate takeaway?
I mean, it's great. It was a surprise because there were so many great companies, and I would have actually granted it to everyone, and that's what Sujatha alluded to. So we did really bond within the group, and I think I'm not exaggerating if I say that there were friendships that were created in the past 6 months. We were here, once a month for a week, so we really did bond. And I would have been happy for anyone to win it. And when, the winner was announced last, so there were already 4 companies who won something, 6 left. So you don't expect that you're the one because there were so many great other companies that were still in the running. So, I mean, I'm super hyped and super excited. And this is definitely a big boost for us.
Not everyone wakes up, has lunch, and then finds out that they've received $1 million follow-on funding. Although not everyone deserves it as you do it, and that is the beauty of Luminate. You care to disclose any plans for scale-up or how the funding can be used?
Well, the funding, I mean, we're now building the next prototype that we want to use as a demonstration tool to get purchase orders on it. And so that's the next goal. This funding obviously is also connected to developments here in New York State and the US. So we now can promote these earlier than we would have planned without the funding. So yeah, I mean, the next goal is really to build something that we can sell. We have a prototype in the lab, which we can use to actually do cutting as a service. But the goal is for us to sell machines, and that's the next big milestone for us, build this machine.
And Sujatha, I'll end with you here. Cohort 6 applications are open. Again, every cohort is different in some ways, similar in some ways. What are you hoping for to see in applications for the next cohort?
Well, it's kind of fun because I never know. It's like it's Christmas and I open up the box to see what interesting applications come our way. But I want people to think really innovatively, think about what really is next. And it might be something in quantum, and it might be something in image processing. I just don't know. I look for the sheer joy of discovery. Sheer joy of discovery. Well, congratulations to you, Alexander, Sujatha. Thanks always for the time. Congratulations to you both, and we will see you again soon. And again, probably before October, when we crown Cohort 6 winners. Great. Thank you. Thank you.
Thank you.
Through Luminate New York, Lydrotech was introduced to AIM Photonics. The collaboration is helping Lydrotech build the infrastructure for developing the next iteration of its technology and to execute on its plans to establish U.S. operations. AIM Photonics hosts and supports Luminate Accelerator companies, encouraging collaboration, especially for those in the semiconductor industry. Luminate has also collaborated with Optica since 2020, helping to bring the accelerator companies to a wider audience worldwide. You never really know who you'll bump into on the trade show floor. It's something that is as much a joy as it is a benefit of in-person trade shows. Plenary and technical sessions, on the other hand, are guided by a program. So when Frontiers in Optics and Laser Science released its technical program, attendees no doubt paid particular notice to the chance to catch up research update from the Nanoscale and Quantum Photonics lab at Stanford University. Headed by Jelena Vuckovic, the laboratory is one of the country's most active photonics changemakers. Vuckovic, a United States Department of Defense Vannevar Bush Faculty Fellow and inaugural director of the Q-Pharm Initiative based at Stanford and SLAC, leads a group whose research endeavors, and recent commercial pursuits, span advanced developments in quantum information science and quantum optics. In the area of material science, the group and its members have placed considerable focus on silicon carbide. The material holds promising optical addressable spin defects, and from that and other properties, holds vast potential for scalable integrated photonics. Daniil Lukin has helped lead the Nanoscale and Quantum Photonics lab's work in this area, and representing the lab he headed east to Rochester to present on scalable semiconductor quantum systems. We caught up with Lukin before his presentation to chat about the Vuckovic lab and his latest work, and how both encapsulate much of the dialogue at the conference. Daniil, thank you for being here. You know, a lot of the talk at the conference, we were just saying off air, so far, both at the exhibition and on the industry side as well, and even from those in R&D, has been on, I guess, this pyramid, I suppose, of quantum applications. So from the top down, you have quantum compute, and then in some order beneath that, sensing, networking, timing, and timekeeping, and the list goes on from there. That feeds into your presentation a little bit. Tell us about what you're going to be speaking on here in Rochester.
I will be primarily speaking about our quantum photonics work in silicon carbide based on color centers in the material. So the idea here is that the material hosts, one can say, artificial atoms, which are vacancies inside the crystal, and they have many properties that are similar to atoms, but they are embedded in the photonic circuit, and you can get a lot of benefits technologically from that, as opposed to atoms that are just suspended in vacuum in more traditional AMO experiments.
You know, material science, of course, is another maybe sub-focus of the lab in which you work out at Stanford. And you and your team published an Optica paper looking just at silicon carbide, of course, last year, and that factors into the presentation you're giving tomorrow at FIOS. Can you give us the rundown on what that work entailed and what your group has found out on silicon carbide? And the second part of that is what applications are supported by that work?
Yes, absolutely. Sort of the work that we do in our group that I'm involved in, it can be divided into two categories. One is what I'll be primarily speaking about tomorrow, which is the quantum applications with defects in silicon carbide. And that was really the motivation for us to study silicon carbide photonics, to be able to harness the photonics capabilities of the material in conjunction with the defects. But along that path, we took a big detour to develop the more classical nonlinear photonics capabilities in silicon carbide, and that's what that paper that you're referring to did. What we have been able to show is to improve the fabrication method for the thin films of silicon carbide in order to get to a sufficiently high quality material that would hit the threshold at which you can do nonlinear optics. So the paper that you're referring to demonstrated the first optical parametric oscillation, the generation of other frequencies of light spontaneously from one frequency of light. The first demonstration of frequency combs in silicon carbide.
Frequency combs have been a popular discussion point, both on the exhibition floor and in sessions here at the conference. And it's really been the continued investigation of frequency combs. In fact, the commercial rollout of combs has been a real theme here as well. And I think part of that has to do with the types of companies that we're seeing on the exhibition floor. Your group is one of the first actually to investigate the quantum optical properties of solid-time microcombs. I'm not going to ask you specifically about that work, but can you just speak a little bit to the progress that we've made in microcombs? And is it fair to say that we've arrived at a point in which the potential is really feeding into the reality of what these devices can do?
So, the work that you're referring to on the quantum optics of frequency of solid-time microcombs is the work that we have co-authored together with Melissa Guidry and Keel Yang. And the idea there is well, as we were on that, so to say, side path of improving photonics, and it's side path because it wasn't necessarily directly applied towards quantum initially, but the final destination is low-loss photonic circuits for quantum applications, and as part of it we developed frequency combs and solitons in silicon carbide, and then we looked at the charts and realized that they were one of the most efficient in the world of all other platforms, and then we combined our expertise in classical and quantum photonics in order to look at the quantum properties of the frequency combs. And so with regard to the potential and where we are today, I think that we are very far from harnessing the full capabilities and potential of solitons and frequency combs for technology, because not because we haven't done much as a society, but because there's a lot of potential. And even more so, there is a tremendous amount of things to learn from the fundamental side, both classically and from the quantum perspective. And I think that solitons, dissipative solitons in resonators, which have only been discovered less than 10 years ago, are really a wealth of excitement, both fundamentally and for applications.
Fair enough. The Nanoscale and Quantum Photonics Lab in which you work represents one of the more dynamic photonics working groups in the country. I think that's fair to say. Tell us about what's going on in the group now and what we can expect from you and your colleagues.
Well, we have a lot of things going on in our group, and the work that we briefly covered here on silicon carbide, quantum, and nonlinear photonics is just a small section of that. We work on a variety of things, including on diamond quantum photonics, so very similar to the work that we do with silicon carbide, but I would say much more further along because of some excellent properties of diamond that are really unrivaled by any other material in terms of the quantum qubits in it. And in addition to that, we have a variety of work on inverse design of photonics, where we apply state-of-the-art computational methods to allow the computer to design the best possible performance devices that no person could ever design just with a ruler and compass. Inverse design has been applied to a variety of things in our group, including accelerators and frequency conversion of light, etc.
Well, Daniil, have a great conference. I appreciate the time. Best of luck in the presentation, and have a safe trip back to the West Coast.
Thank you very much, Jake.
That concludes this week's episode of All Things Photonics. Thank you to our engineer, Alan Shepard, and to our news editor, Jake Saltzman, as well as to this week's sponsors. Our featured music is courtesy of betterwithmusic.com. Most of all, thank you, our listeners. As always, you can share your thoughts, pitch us ideas, and let us know how we're doing. You can reach us at allthings@photonics.com. All Things Photonics is available on all major platforms, including Spotify, Apple Podcasts, as well as on our website, photonics.com.